Hi, my name is Tom and this is the second video of level 19 out of 30 easy steps to understand everything about Einstein's special relativity. I'm assuming you have seen the first video of level 19. So without further ado, GP, hit it! Level number 19, episode B, the one for the daredevils. In the first level I gave an introduction about the person Hendrik Antoon Lorentz and the trouble with light which he fixed. Now we will look a little bit more at the math behind it. And this is for daredevils. Still, I don't think it's really difficult math. It's, I would say, high school math. You can follow, but you have to have a little bit more perseverance. You have to be a daredevil. So there we go. Yeah, this is what the trouble with light. Hendrik Antoon Lorentz. Just a small recap. You know, he's Dutch. I made it very clear. I'm proud of him. And he was born in Arnhem, the same city I was born in, etc., etc. Einstein was really crediting him for special relativity. And he said, for me personally, Hendrik meant more than all the others I've met on my life's journey. And Poincaré, which published the solution of Hendrik in 1905 and dotted the I, also says, you know, the most satisfactory theory is that of Lorentz. So Lorentz is really a special person. If we look at Galilean relativity, we've seen it in very many levels before. We talked about events, and then I introduced my special secret notation. The one that will scare the evil mathematicians, because with this way of writing things down, you almost can't go wrong. And that's something evil mathematicians don't like, you know. They want to be mysterious with their evil symbols and abbreviations, and you know, the deeper you get in, you have no clue what you're doing at all. But I want to be very specific about who's talking about what. So if an event is written down by an observer and he writes down its X location, we will always write down X of what, the event, comma, from which perspective. So now we know who's talking about what. The same for time and the same for velocity. So I will be rigorous about this and always use these way of noting things down. So here we have an event and we have three observers in this example, and they all three write down when they saw the specific event. Let's say the event was a light flash. And observer 1 says it was 100 meters away from me and it happened at 30 seconds or something, you know. He writes down the time. And the observer 2 does the same and observer 3 does the same. And these three observers are all on the same track, you know, the same railroad, you could say, and they are all traveling with their own constant velocity relative to the ground. Because special relativity is one-dimensional and only allows constant velocities for the observers. And well, you did this. We did experiments and you were able to derive these equations. And let me just read it out loud, you know, because it maybe looks complicated, but it's not. It's just a story. The x-coordinate of the event through the eyes of observer 2 equals the x-coordinate of the same event through the eyes of observer 1 minus the velocity of observer 2 through the eyes of observer 1 multiplied by the time of the event through the eyes of observer 1. You might say, oh, I'm lost here. No, you can do this in your car on the highway. This is really, really easy. And if you want to practice, go back to levels number 5, 13 and 18. The time, well, time is just time. You can also go from observer 1 to observer 3. It's the same equations, but instead of the velocity of observer 2, you put in the velocity of observer 3 through the eyes of observer 1, and you get these equations. And you could also go from observer 2 to observer 3, and putting in, and again, another velocity. So this is just switching perspectives between the different observers using the equations of Galilean relativity, which makes total sense. There are also some rules. The velocity of something from the perspective of something is always zero. As said in Einstein's special relativity, all observers are moving at a constant velocity relative to something else. So there are no accelerations. So if you close your eyes, you will never be able to tell if you're moving fast or slow or whatever. It feels like you're not moving at all. And that's also how these observers act. They say, I'm not moving. All the other stuff is moving around me, but I'm not moving. My velocity is zero in my world. Another rule is that if I say to someone else, observer B, you are moving away from me at 30 meters per second, then that observer B could say, well, that's not true, Tom. I'm not moving at all. You are moving away from me 30 meters per second in the other direction. And that's where the minus sign comes in. So the velocity of something A through the eyes of B is minus the velocity of B through the eyes of A, right? And then the third rule is, we did this in the previous level with the animations. The velocity of something through the eyes of B is the same of the velocity of that same something through the eyes of C, plus the velocity of C through the eyes of B. So you can chain these velocities and add them all together. And this is Galilean relativity. It might look complex in math, but if you do the examples, it just makes total sense. It's easy. It's really easy. And now we have trouble. Light doesn't work that way. If you put in two light flashes, if you put in a ray of light, which is traveling at the speed of light, and you ask observer 1, observer 2 and observer 3 to write down their observations, they will break Galilean relativity. They will not, you cannot do this with these equations. You will see that if you run towards the light, Galileo will tell you the speed of light through your eyes will change. If you run away from the light, the speed of light will change through your eyes. But the experiments tell us that doesn't happen. It's always the same. It's so not intuitive. But no matter what you do, how fast you're going, the speed of light is always the same. So we need new formulas. They break these Galilean relativity equations. And they also break rule number 3. Because if you are A and the velocity of the ray of light is B, you cannot add these things together. If two observers are going head to head, and they are almost at the speed of light, and this one also has almost the speed of light, their relative speed is not almost twice the speed of light. No, it's still the speed of light. It does not make sense at all. So Galilean relativity makes really sense. Light totally breaks logic. Lorentz came to the rescue. In the previous level, we saw that he and many others did. And what they did is, I'm using the same notation. These are the new equations. They are a bit similar to the ones from Galileo Galilean, but they look a little bit different. And I'm just going to speak out the first one, going from observer 2 to 1 or from 1 to 2 for the location, the x, the first equation on top of this sheet. The x coordinate of some event according to observer 2 equals gamma 2, 1, which is the Lorentz factor. I will talk about this shortly, some constant, multiplied with, between brackets, the x-coordinate of the event through the eyes of observer 1 minus the velocity of observer 2 through the eyes of observer 1 multiplied by the time of the event through the eyes of observer 1. So you see it's almost the same as the Galilean relativity equation, except for the gamma factor. And for time, it's a little bit more difficult. It says the time of the event through the eyes of observer 2 is the same gamma multiplied by the time of the event as seen through the eyes of observer 1 minus the velocity of observer 2 through the eyes of observer 1 multiplied by the x-coordinate of the event through the eyes of observer 1 divided by the square of c, in which c is the speed of light. This is totally different than in Galilean relativity. In Galilean relativity we say, well, time is time. Everyone has the same time. If you synchronize your clocks, then time will always be the same time. It doesn't matter which observer you are. You all have the same watch and you all see the same time. Lorentz said, no. Time can be really different. If you start moving relative to someone else, your perception of time, your reality changes. And the bad news is you will not notice unless you compare notes. So this is really, really special relativity. It's just mind-blowing. This is the gamma. The gamma is a constant, and this constant is a function of the velocity between two observers. So if you have observer A and observer B, and then there is a relative velocity between these two observers, you put in this equation and you get gamma, which is a constant, and c is the speed of light. It's there as well. This is the Lorentz transformation. This saves the day. This makes us able to model all the experiments we've done so far. Rule number 1 still stays there. Everyone is saying, I'm not moving, you are moving, and they are all right in their reality. If I say you are moving away from me at 30 meters per second, we can switch perspective. You can tell me I'm moving away 30 meters per second in a different direction, hence the minus sign. Rule number 3, no. Rule number 3 is totally broken, and we will fix this in level number 29. Now the evil mathematicians. You know, well, at many levels I told them they are evil, and I tell you why. This is what we just came up with, the Lorentz transformation. For me, you know, it doesn't look sexy, I would say, you know. It has a lot of words and letters in there, and they are complete stories, right? You have to read it out loud and it's a complete story. So what did the evil mathematicians do? No. Let's write it down like this. So if you go online and you search for Lorentz transformations, you will get to see these equations in the pink, orange, reddish square. They use these accents. And in previous levels I told you these accents could also be a time derivative. It's just horrible. It's horrible. You can't say who's talking about what? What time? X of what? By whom? Which velocity? Honestly, using these equations is like going into the jungle after watching one episode of survival training. You know, you saw like 50 minutes of survival training, and then they drop you from the plane in the jungle with real lions. You will get eaten alive. I got eaten alive. I made so many mistakes using this syntax, this way of writing things down. And it took me, I think, months when I changed the notation into the one that's on the bottom. And then I hardly made any mistakes because I know exactly who was talking about what. It feels like, you know, you're meeting with a kitten instead of the hungry lion. So my advice to you all is, if you start to proceed on this mountain, forget about the popular way of writing down Lorentz transformations. Always use the one that I propose, so you will always know who's talking about it. I want to thank you for watching the B level. It is an optional level. You could have gone straight to level number 20, but you chose otherwise, and I thank you for that. GP, hit it!